Hello everyone, I'm Vincent. Today, my group is going to present the advanced catalyst application in petroleum refineries. Petroleum refineries is an industrial process plant where crude oil is transformed and refined into more useful products such as gasoline, kerosene, liquefied petroleum gas, jet fuel, and fuel oil. However, the global refining and petrochemical industry are facing increasingly more difficult technical challenges due to stricter environmental mandates and more demanding product quality specifications. In order to confront these challenges, the most cost-effective and efficient way is through the implementation of newer catalyst technologies which help to debottleneck the refining process. In the later part of this video, we are going to look into 6 types of petroleum refining process and the application of advanced catalysts in them. Without further ado, let's take a look at the hydrodesulfurization process. Hydrodesulfurization process is used to reduce sulfur level of fuels in the presence of catalyst. This is extremely important because the combustion of sulfur-containing fuels will release sulfur oxide, causing atmospheric pollution and acid rains. Moreover, the catalysts used for processing of oil products have low tolerance to sulfur. At the end of hydrodesulfurization process, sulfur compounds are converted to hydrogen sulfide and hydrocarbons. In the conventional hydrodesulfurization catalyst, it includes a transition metal such as molybdenum or tungsten promoted by cobalt and nickels, and also a solid support such as alumina, silica, or zeolites. The utilization of advanced hydrodesulfurization catalysts enable the reaction to be carried out under mild conditions with high selectivity and stability. However, there are 3 expected properties of catalysts, which includes high desulfurization activities, high nitrogen and metal atom removal abilities, and also high selectivity for desulfurization. The advanced catalysts that involved in the hydrodesulfurization includes star catalyst, nebula catalyst, and sentinel catalyst. Star catalyst was developed by using superactive Como and Nemo catalyst. Como star catalyst was used at high level sulfur stream, whereas Nemo star catalyst were used as low sulfur streams. On the other hand, nebula catalyst is a bulk-based metal catalyst without using a porous support, and it can work under harsh conditions. Last but not least, the sentinel catalyst. Sentinel catalysts are produced by modifying the preparation methods of the traditional hydrodesulfurization catalyst. Nemo sentinel catalyst was used at low sulfur level stream, whereas Como sentinel catalyst was used at high sulfur level streams.
Hi, I'm Julia, and I'm going to talk about catalytic cracking. Catalytic cracking converts complex hydrocarbons into lighter products such as LPG, gasoline, naphtha, kerosene, and diesel. It is classified as moving bed or furnace bed units. Moving bed units are represented by TCC, while furnace bed units are represented by FCC. FCC is widely used catalytic cracker in this process. In FCC, the furnace catalyst helps to transfer heat from the regenerator to the oil feed and reactor. There are 2 types of FCC units in use today, which are side-by-side type and stack type. For the side-by-side type, the reactor and regenerator are placed adjacent to each other, while for the stack type, the reactor is mounted on top of the regenerator. There are 3 classes of commercial cracking catalysts, which are Class 1 acid-treated natural aluminosilicates, Class 2 amorphous catalysts, Class 3 zeolite catalysts. And most commonly used catalysts are Class 3 or mixture of Class 3 and Class 2. Zeolite catalysts are better than amorphous catalysts because of their high cracking activity and can prevent overcracking of gasoline to gas and coal. And most common types of zeolites in FCC are X, Y, and ZSM5. These are the advanced catalysts and their benefits or application in this process. By adding metal additive of iron, antimony, copper system to catalyst, this can reduce nitrogen oxide emissions. Rhodium supported anionic clay can reduce carbon monoxide emissions. Mixture of Y zeolite, ZSM5, and metals can increase propylene, light olefins, and lightweight yield. Crystalline aluminosilicate, sodium, potassium, and rare earth content together with a xenon absorption can increase the octane number of gasoline. And last, combinations of HZSM5, USY natural clay and binder can produce less dry gas byproducts. That's all from me. Thank you.
Hello, my name is Eugene, and today I'm going to talk hydrocracking in petroleum refinery. Hydrocracking is used for the conversion of a variety of feedstocks to a range of products by adding hydrogen and removing impurities in the presence of a catalyst. Convert heavy fractions to lighter cuts at low temperatures and under high hydrogen partial pressures, leading to inhibit rapid catalyst deactivation, which requires continuous regeneration of the catalyst during operation. There are two types of catalytic sites in hydrocracking, which is acid sites and metal sites. The acid sites provides for the cracking and isomerization and consists of amorphous oxides and crystalline zeolites plus binder or mixture of them. Whereas for the metal sites, it provides for the olefin formation and hydrogenation and consists of noble metals or non-noble metal sulfides from group 6A and group 8A. There are four advanced catalysts which I want to highlight in this hydrocracking process. First is the iron supported on active carbon. It requires relatively low hydrogen pressure, which is 7 to 10 megapascal, and it can prevent hyperbolic condensing and also achieve high conversion with low coke yield. The next is the NEMO supported on gamma aluminum oxide. It has a higher percentage of C17 and C18 hydrocarbons, thus has a higher certain number. The third is the platinum zeolite. The strong acid sites which produce isoparaffins that are desirable in diesel to have a lower pour point. Last but not least, which is the molybdenum supported on aluminum oxides, the increasing decomposition of vacuum residue and decreasing coke decomposition.
Hi, my name is Zachariah and I'll be presenting about catalytic hydroisomerization. So this technology uses a special catalyst to very selectively place side chains on the longer loop range paraffins. This process improves the lubricant and distillate fuels as well as becoming a key process to improve research octane numbers of the final gasoline. There are three types of isomerization processes. The first one would be the high temperature process, the medium temperature process, and the low temperature process. For the high temperature, reactions are generally promoted by fluorinated alumina, whereas the medium temperature reactions have been reported to be promoted by zeolites, while chlorinated alumina is utilized at low temperatures. Next, I will talk about the advanced catalysts and their benefits. The first one would be zeolites. Although it requires a higher operating temperatures compared to other catalysts, these catalysts possess a high resistance to impurities in the feed and can be regenerated more easily as compared to chlorinated alumina. Next one would be platinum or zirconium 4 sulfate. These catalysts demonstrate good properties and activities for the isomerization process. They are resistant to catalyst poisoning and can be regenerated in a similar way as zeolites.
Hi, my name is Said and I'll be talking about catalytic naphtha reforming. In catalytic naphtha reforming, we're basically converting low-octane naphtha into high-octane naphtha reformants, where the high-octane naphtha reformants can be used in petrochemical feedstocks. We basically have three types of catalytic reforming: semi-regenerative catalytic reformer, in which the plant needs to be in shutdown in order for the catalyst to be regenerated. We have cyclic catalytic reformer, in which we have another catalyst as a spare, which can be used while the original catalyst is being regenerated. We also have continuous catalyst regeneration reformer, in which just a portion of the catalyst needs to be regenerated continuously while the plant is in operation. We have common catalysts in catalytic reforming, some of which are in monometallic, where they only consist one metal. We also have bimetallic, where they consist of two metals, and trimetallic, where they consist of bimetallic and another metal. In advanced catalyst, and the benefits is multimetallic catalyst supported on chlorinated aluminum. For example, one of the example is the trimetallic. In high purity alumina, it provides high resistance to erosion, while the platinum provides high selectivity and stability. High regeneration ability of this catalyst complies with the need of continuous catalytic reformer regenerator. Thank you.
Hi, I'm Vasantha. I'm going to explain about the catalytic hydrocarbon steam reforming, which used to produce the hydrogen gas from the hydrocarbon component. There is a major process involved in this process, which is the steam reformer. Steam reformer is used to remove the catalytic poisons such as sulfur, chloride, olefin, arsenic, mercuries, and metals. And there are some advanced catalysts used in this process, such as nickel with ceramic support used to reduce the potential for the carbon formation, and calcite used to catalyze carbon gasification. Potash promoted catalyst used to avoid the carbon formation over the catalyst life. And there are three types of catalytic conversion catalyst, such as a non-alkalized catalyst, mildly alkalized catalyst, and third layer of highly alkalized catalyst. And there are also some customized alkyl catalysts with a quadrolobe shape used to increase the catalyst activities. And all those catalysts are used to design to minimize the rate of carbon deposition and maximize the rate of carbon gasification. So thank you.